main objective of this program is to identify whether a given square matrix is magic matrix or not. In order to say a matrix is a magic matrix, it should have the following properties. That is, no two elements of it should be same. That is, it should be unique matrix. Already we have explained how a matrix is a unique matrix or not, how to find out that one in the previous examples. The same thing can be used in this problem. In addition to this uniqueness, one more extra quality the matrix has to satisfy. That is, its row sums, column sums, and diagonal sums all should be same. If both the conditions are satisfied, then only the matrix can be called as a magic matrix. Here in this problem, we have attempted second part only, as already the first part is discussed in the previous examples. Here we propose first to calculate the sum of the elements of the both the diagonals, that is the principal diagonals and the other diagonal, that is off diagonal. If they are not same outrightly, we can say the matrix is not magic matrix. Otherwise, we calculate the row sums and column sums and compare with the one of the diagonal sum. So in this example, we have taken the principal diagonal sum. With that one, we are going to compare. If every row sum and column sum is same as the diagonal sum, then we can say it is a magic matrix. Otherwise, we can say not a magic matrix. Thus, we have written two for loops. Each time, ith row sum, ith column sum is calculated, and it is compared. They are compared with the principal diagonal sum. If any one of them are not same as the principal diagonal element sum, then I can say, or we can say, it is not a magic matrix. We need not require to calculate next row or next column sums. We can come out. If they are same, then only we need require to calculate next row and column sums. If they are also same as the principal diagonal, then we have to calculate the next row, next column sums. Like this, if all the rows and column sums are same as the principal diagonal sum, then we can say the matrix is a magic matrix. The following slides will explain how the calculations can be done. For the sake of explanation, we have taken a 3 by 3 matrix, and initially S1 and S2 values are assumed to be 0. Then the first for loop starts. When I value becomes 0, n minus 1 minus I, that is 3 minus 1 minus 0 becomes 2. For S1, we'll add AII, A00, that is 2, thus S1 value becomes 2. Similarly, for S2, we will add A of I, n minus 1 minus I, that is A02, that is 1. So S2 value becomes 1. I value will be incremented by 1, thus I becomes 1. N minus 1 minus I becomes 1. Now, A of II, that is 4, is added to S1, thus S1 becomes 6. Similarly, A of I n minus 1 minus I, incidentally both I and n minus 1 minus I are 1s. So A11, that is 4, is added to S2. That S2 value becomes 5. I value will be incremented by 1. Thus I value becomes 2. The n minus 1 minus I value becomes 0. A of I is added to S1. That is A22. That is 7 is added to S1. Thus S1 value becomes 13. A of I n minus 1 minus I is added to S2. That is A20 is added to S2. That is 3 is added to S2. Thus S2 value becomes 8. Like this, we have calculated sum of the principal diagonal elements, that is 13. That is 2 plus 4 plus 7. Similarly, off diagonal element sums 1 plus 4 plus 3, that is 8. Now incidentally, S1 is compared with S2. That is the principal diagonal element sums and off diagonal element sums are compared. They are not same. Really, we need not require to compare any row or any column sums. We are required to calculate and compare. Outrightly we can say this is not a magic matrix. However, for the sake of explanation, we are going to continue in the next slides and explain how the next for loops are going to execute and calculate the row sums and column sums. I value is initialized to 0. That is, we are interested to find out 0th row, 0th column sums of the matrix. S2, S3, they are taken as zeros. S1 we are not disturbing, as we require to compare the row sums, column sums with sum. That is the reason why we are taking the principal diagonal sum S1, we are not disturbing it. S2 we are reusing it. Aij, that is 0 0, A0 0, 2 is added to S2. Similarly, Aji also 0 0, that is 2 will be added to S3. That is S2 becomes 2, S3 also becomes 2. J value is incremented by 1. Aij, that is A01, that is 3 is added to S2. Thus S2 value becomes 5. Aji, that is A10 is added to S3. That is 5 is added to S3. S3 value becomes 7. J value is incremented by 1. Thus J value becomes 2. Aij, that is 02. A02, 1 is added to S2. Thus S2 value becomes 6. Aji, A20, that is 3 is added to S3. Thus S3 becomes 10. Now S2 contains 6. That is nothing but 0th row element sum. S3 contains 10. That is the 0th column element sums of the given matrix. Now these two things are compared with S1. If both of them are same as S1, then we can go and find out the next row and next column sums. However, incidentally in this example, none of them are same. So we can outrightly say the matrix is not a magic matrix. We can come out. Like this, we can calculate row 2, column 2 sum, row 3, column 3 sums, and compare with S1, the principal diagonal sum. If any one of them are not same as S1, we can outrightly print it is not a magic matrix. We can simply print no and come out from the program. If all of them are same, then the last printf statement will be executed, indicating that it is a magic matrix. Like this, here we have calculated first two diagonal sums, and they are not same. We outrightly said there itself it is not a magic matrix. If they are same, then only we have tried to calculate the row sums and column sums. If any row sum or column sum is not same as S1, the principal diagonal sum, there itself we can outrightly say it is not a magic matrix, and we can come out without calculating any other rows and column sums. Like this program works.